Hello and welcome. Today I've decided to take up the challenge of going through one of the most beautiful, fundamental, elegant proofs in calculus, the power rule. A little bit of a background story. I was trying to teach this to my grade 12 students this year, and I found out that not too many of them were familiar with the binomial theorem. The binomial theorem is a theory that helps us expand a binomial raised to any power in one step. And knowing the binomial theorem will make understanding and going through this proof a breeze, really. So I decided to take a different path this time, and I'm going to start by using Pascal's triangle to expand the binomial theorem, which is a less sophisticated way than the binomial theorem, but it's simpler and it does the job just fine. And I'm going to try to go over it as slowly as I can and as clearly as I can, as fast as I can as well. So let's get started. So when I first heard about the Pascal's triangle, first sentence I was introduced with was, it's a triangle so easy to build, even a child can create it. So that gave me a little bit of confidence that I would be able to understand it, but it is true. Look at how it works. So you first start with number 1 and you write it on top of the triangle. And you build the next row by adding the numbers above, so in the above row, which means that here you're adding number 1 to 0 to create 1, number 1 and 0 create 1 in here. Now, next you build the second row. Remember, this is the 0, row 0. This is row 1. Now we're going to move on to row 2, and we go 1, because we have 1 plus 0, 1. Now 1 plus 1 equals 2. 1 plus 0 equals 1. In the next row we have 1, 3, 3, 1, which means 1 plus 0, 1. 1 plus 2, 3. 2 plus 1, 3. 1 plus 0, 1. Next, 1, 4, 6, 4, 1. So 1 plus 0, 1 plus 3, 3 plus 3, 3 plus 1, 1 plus nothing. I know you're getting tired of this. We're going to go a couple more rows. 1, 5, 10, 10, 5, 1. Again, 1 plus nothing, 1 plus 4, 4 plus 6, 6 plus 4, 4 plus 1, 1 plus nothing. One more. 1. We need to see a pattern, that's why. Then 6, 15, 20, 15, 6, 1. We need to have enough numbers. So we can continue on forever, obviously. Okay? But before I move on to the last row that I want to write in here, I want us to recognize or to observe some patterns. Notice that the first number on the side of the triangle will always be 1. And the last number here in the triangle will be 1. So the last number in each row would be 1, and the first number will also be 1. Okay? Now here goes the next pattern that I want us to observe. Remember that we named the row starting with row 0. So this is n equals 0, we say. The next row is row 1, n equals 1. The next row is row 2, n equals 2. And then we continue, n equals 3, n equals 4, n equals 5, n equals 6, and I will dare to go one more last row, I would say, n equals n. So we can stop whenever we want. Okay? Now, when we look at the second number in each row, so here's the second number in row 1, second number in row 2, second in row 3, second in row 4, second in 5, second in 6, right? you will see that the second term will match the row number. So we have the row number as a second term, and we will also have the row number as a second last term as well, because they are the same, right? Okay, so now we are going to start with a real expansion. Now, a binomial can be in the form a plus b to the power of n. That's a general form of any binomial, right? And then we are raising it to the power of n, and we are trying to expand by using this beautiful triangle. So I'm going to start with a plus b to the power of 0. We know that if you bring anything to the power of 0 would equal 1. Okay, anything but 0. So as you notice in here, we have just number 1 in row 1. Now next, we have a plus b to the power of 1. We know that this would be simply a plus b. If we have a plus b to the power of 2, so n equals 2, we know how to expand this. A squared plus 2ab plus b squared. If n equals 3, we should know this expansion. If you don't, stop the video and try to expand a plus b times a plus b times a plus b, okay? And we will get in here a cubed plus 3a squared b plus 3ab squared plus b cubed, okay? Now, once we have expanded the binomials up to the power of 3, I want us to look at some patterns together. So, in the expansion of a plus b to the power of 1, we got a to the power of 1, b to the power of 1. So, it would be safe to say that we can place the terms a and b in row 1. That's a power 1, remember, okay? In row 1 of the Pascal's triangle. Now, a plus b squared, we have a squared plus 2ab plus b squared. This is what we're going to do. That would be a squared plus 2ab plus b squared. So notice how the coefficients in the expansion will match the numbers in Pascal's triangle, okay? Now next, we have a to the power 3, 3a squared b, 3ab squared b cubed. So it will be safe to say that we can place all these terms right here. A to the power 3, 3a squared b, 3ab squared, b to the power of 3. So the coefficients of the term in the expansion, always organized in standard form, okay, will fit in the numbers of Pascal's triangle in the respective rows. Another thing that I would like us to take a look at and focus on is the degree of the term. Remember that the degree of each term in the expansion will be degree 3 for a, degree 2 plus 1 for the second term, so degree 3, degree 1 plus 2, degree 3, b to the power 3 is third degree as well. So the degree of every term will match the number n in here, so the power or the row number, okay? Another very important observation that we have to make in here is the fact that we always start with the first term raised to the highest power. The second term will be to the power of 0. That's why it's invisible, because when b to the power 0 will be 1, multiplication by 1 doesn't change the value of the term. Now, in the next term, a will lose a power, so it will go from 3 to 2. B will gain a power, so it will go from 0 to power of 1. The next term, a will lose another power and b will gain a power. And in the last term, a will have no power, so it will be power of 0, and b will be to the highest power, power of 3. So for the expansion of a plus b to the power of 4, then, we are going to very safely say that this would be a raised to the highest power, b to the power of 0, and then we will have the next term, a to the 1 power less than 4, that's 3, b to the power of 1, so b is gaining power. It was 0 here, right? And now we have the next term, a will lose a power, b will gain a power. A will lose a power again, b will gain a power, and the very last term will give all the powers to b, so b to the power of 4. If n equals 5, we continue in the same fashion. So this will be a to the power 5. The last term will be b to the power of 5. So we have a losing a power, b gaining 1. A losing a power again, b gaining 1. And so on and so forth. And the power of every term would be 5, the same as the row number. So a, b, 4, and so on. In the same way, here we have a to the 6, b to the 6 at the end. And since we're here, we're going to do the row n. So in row n, we will have a to the power of n, and we'll end up with b to the power of n. So the next term must have the coefficient n, right? So we have number 1 here, number 1 here, and before it we'll have the coefficient n. That we know for sure. The rest will depend on how far down the triangle we are. So the next term here would be a to the power of n minus 1, and then b will be, minus 1, b will be to the power of 1. The second last row would be a to the power of 1, b to the power of n minus 1, okay? Now, again, the rest of the terms in between can be unpredictable because it will depend on how far down the triangle are. But here we are. We have the first, the second last, and the last term. That's all we need to understand the power rule. So let's keep this in mind, and let's take this to our proof. Okay, we will implant this idea very soon in here. So we are trying to differentiate f of x equals x to the power of n. We're proving this for n positive, okay? And we're going to prove that at x equals a. We can prove it at any value of x. Now remember that to find the derivative of any function, the most basic way of deriving it will be by using the first principles formula. And here goes the first principles formula waiting for us to be used. Now, remember that what we are trying to do here is differentiate. So which means that we are differentiating f of x equals x to the power of n. And the derivative, which I said, is the limit as h approaches 0, f of x plus h, take away f of x divided by h. So we're going to create a function based on f of x equals x to the power of n. We will create the function f of x plus h. Okay? So remember, what we have done in here is only one thing. We are replacing x with x plus h. So we will rewrite this as the limit as h approaches 0 of x plus h to the power of n Now take away f of x. Now remember that f of x, oopsie, here. So this is f of x. F of x will be x to the power of n, right? That's what we were given there. So that's what we are deriving, x to the power of n. And this will be divided by h. Now our job is to expand x plus h to the power of n. So we'll do this very easily now that we kind of went through the binomial theorem. And we kind of understood, I hope, how it worked. So here we go again. X plus h to the power of n will have the first term x to the power of n, the coefficient 1. H will be to the power of 0. Now, the second term, we know that it will have the coefficient n, because remember that we said it will be n, the same as the row number, right? Because that's what happened in the Pascal's triangle. So the second coefficient was equal to the power. So we have n that multiplies, x will lose a power, h will gain a power. And then we can continue on forever. Well, forever it depends on how big our n value is. And we'll arrive to the last term, or second last term, I should say. So the two last terms in here, okay, will be the second last n, coefficient n. The first term in the binomial will be to the power 1, the second to 1 less than n. So that means we have n, x will be to the power of 1, h will be to the power of n minus 1. And the very last term will have a coefficient 1, and h will be to the highest power, power of n. So what we have just done in here is expand x plus h to the power of n. So this is all x plus h to the power of n. And what we want to do is take away f of x, and f of x is x to the power of n. So we're going to take that away right here. So minus x to the power of n divided by h. So this is the most exciting part of the theorem now. We will simplify. I want you to listen carefully. So remember that all these terms in here, right, are in the numerator. You can add and subtract the like terms. The only like terms I see so far are x to the power of n and negative x to the power of n that simplify to 0, okay? So because x to the n minus x to the n is 0. So look at what we are left with. We're almost at the end of it, so patience. H approaches 0. So the first term is nx to the power n minus 1 times h. And then we have plus many, many terms in here. And then we have nx to the power 1, h to the n minus 1, and then plus h to the power of n, and everything here above h, or over h here. Now, I want you to think a little bit. Notice how the first term will have, I'm going to choose a different color here, all right. So it will have an h as a factor, so it's multiplied by h. And we can safely say that the last term has a factor h as well, right? And this term has a factor h as well. It doesn't look like h, let me make it clear. So that's an h as well, right? And imagine all the terms in between. Would all the terms in between have an h in it as a factor? Well, let's take another look at Pascal's triangle here. So notice that you start with, say for example in row 5, a to the power 5, b starts appearing in the next term, and it will be present in every term because it's still gaining power. Now, our h is in the same role, in the same place in here. So we imagine that all the terms in between will have an h as a factor to some power, okay? So it would be safe to say that the limit as h approaches 0 can be actually written in factored form. Take h out, and the very first term will be left nx to the power of n minus 1. And then here, remember that the next term will have h squared, so you will have some h left. The next term will be h cubed, and the next term will have an h4, right? And other stuff, obviously, right? But we are interested in h in here because we are trying to take out h, okay? So all the terms will have an h. The very last, the second last, will be n to the power times x, power 1. H will be, you took one h out, that would be n minus 1. Okay? And the very last term, you took an h out, no problem. Actually, this is n minus 2. And the last term will be h to the power of n minus 1. So all these h terms here, right, we will lose a power. So h to the n minus 1 will change to n minus 2. H to the n minus 1. But we can imagine how every term in here will have an h left, okay? So this one was h squared, for example. It will have an h left as well, right? So something h and something h squared and so on and so forth. Now everything obviously would be over h in here. So it's time to get rid of h. So it simplifies, that's why. And let's take a look, or let's take another look at our limit here. Well, it's not a simple limit, it's the first principles formula limit, right? So we have n to the power times x to the power of n minus 1. And then you're going to have something here with h, something here with h squared, and so on and so forth. And I'm going to write the second last term, n x h power n minus 2 plus h power n minus 1. Okay? Over 1. So we're going to say, well, what happens now if we substitute h by 0? Well, if we substituted h by 0, then this second term here will be 0. This will be 0. This will be 0 because all these numbers will be multiplied by 0. So we will say that the limit as h approaches 0 here of x plus h to the power of n minus x to the power n over h equals n x to the power n minus 1. And that is the derivative of x to the power of n, or we're going to say that x to the power of n prime, or the derivative of x to the power of n, equals n x to the power of n minus 1. In Leibniz notation, we will say that dx of x to the n would equal n times x to the power of n minus 1. So, ladies and gentlemen, I introduce you now to the power rule proof, and this is the end of the story here. So, I hope this made sense, and I hope you enjoyed proofs. Remember that proofs are very important in building real understanding of math concepts, and I always encourage you to really understand them, because it will make their use a lot easier. But that's it for today. Bye for